Um, but but even the simplest problems that combine something multiplicative, such as the primes, with something additive, such as shifting by 2, separately we understand both of them well. But if you ask, when you shift the prime by 2, can you get how often can you get another prime? It's been amazingly hard to relate the two.
And we should say that the twin prime conjecture is just that it posits that there are infinitely many pairs of prime numbers that differ by 2.
Yes.
Now, the interesting thing is that you have been very successful at pushing forward the field in answering these complicated questions of this variety. Like you mentioned, the Green-Tao theorem. It proves that prime numbers contain arithmetic progressions of any length.
Right.
Which is mind-blowing that you could prove something like that.
Right. Yeah, so what we've realized because of this type of research is that there's different patterns have different levels of indestructibility. So what makes the twin prime problem hard is that if you take all the primes in the world, 3, 5, 7, 11, so forth, there are some twins in there. 11 and 13 is a twin prime, pair of twin primes and so forth. But you could easily, if you wanted to, redact the primes to get rid of the these twins. Like the twins, they show up and there are infinitely many of them, but they're actually reasonably sparse. There's not. I mean, initially there's quite a few, but once you got to the millions, the trillions, they become rarer and rarer. And you could actually just, like if someone was given access to the database of primes, and just edit out a few primes here and there, they could make the twin prime conjecture false by just removing like 0.01% of the primes or something. Just well chosen to do this. And so you could present a censored database of the primes which passes all of the statistical tests of the primes. That it obeys things like the prime number theorem and other things about the primes, but doesn't contain any twin primes anymore. And this is a real obstacle for the twin prime conjecture. It means that any proof strategy to actually find twin primes in the actual primes must fail when applied to these slightly edited primes. And so it must use some very subtle, delicate feature of the primes that you can't just get from like aggregate statistical analysis.
Okay, so that's out.
Yeah. On the other hand, arithmetic progressions has turned out to be much more robust. Like you can take the primes and you can eliminate 99% of the primes, actually. And you can take any 99% you want. And it turns out, and another thing we proved is that you still get arithmetic progressions. Arithmetic progressions are much, they're like cockroaches.
Of arbitrary length.
Yes.
Though.
Yes.
That's crazy. I mean, so this, for people who don't know, arithmetic progressions is a sequence of numbers that differ by some fixed amount.
Yeah, but it's again like it's an infinite monkey type phenomenon. For any fixed length of your set, you don't get arbitrary length progressions. You only get quite short progressions.
But you're saying twin prime is not an infinite monkey phenomena. I mean, it's a very subtle monkey. It's still an infinite monkey phenomenon.
Right, yeah. If the primes were really genuinely random, if the primes were generated by monkeys, then yes, in fact, the infinite monkey theorem would...
Oh, but you're saying that twin prime you can't use the same tools, like it doesn't appear random almost.
Well, we don't know. We believe the primes behave like a random set. And so the reason why we care about the twin prime conjecture is a test case for whether we can genuinely confidently say with 0% chance of error that the primes behave like a random set. Okay, random versions of the primes we know contain twins, at least with 100% probability, or probably tending to 100% as you go out further and further. So the primes, we believe that they're random. The reason why arithmetic progressions are indestructible is that regardless of whether your set looks random or looks structured, like periodic, in both cases, arithmetic progressions appear, but for different reasons. And this is basically all the ways in which there are many proofs of these sort of arithmetic progression type theorems, and they're all proven by some sort of dichotomy where your set is either structured or random, and in both cases you can say something, and then you put the two together. But in twin primes, if the primes are random, then you're happy, you win. if your primes are structured, they could be structured in a specific way that eliminates the twins. And we can't rule out that one conspiracy.
And yet you were able to make as I understand, progress on the K-tuple version.
Right. Yeah. So the one funny thing about conspiracies is that any one conspiracy theory is really hard to disprove. That if you believe the world is run by lizards, you say here's some evidence that it's not run by lizards. Well, that evidence was planted by the lizards.
Yeah.
You may have encountered this kind of phenomenon. Yeah. So
Yes.
so a pure there's almost no way to definitively rule out a conspiracy, and the same is true in mathematics. That a conspiracy that is solely devoted to eliminating twin primes, you have to also infiltrate other areas of mathematics to sort of, but it could be made consistent, at least as far as we know. But there's a weird phenomenon that you can make one conspiracy rule out other conspiracies. So if the world is run by lizards, it can't also be run by aliens.
Right.
So one unreasonable thing is hard to disprove, but more than one, there are tools. So for example, we know there's infinitely many primes that are no two of which so the infinite pairs of primes which differ by at most 246 actually is the current record.
So there's like a bound.
Yes.
On the
right. So there's twin primes. There's this thing called cousin primes that differ by 4. There's this thing called sexy primes that differ by 6.
What are sexy primes?
Primes that differ by 6. The name is much less. The concept is much less exciting than the name suggests.
Got it. Okay.
So you can make a conspiracy rule out one of these, but once you have 50 of them, it turns out that you can't rule out all of them at once. It requires too much energy somehow in this conspiracy space.
How do you do the bound part? How do you develop a bound for the difference between the primes that there's an infinite number of?
So it's ultimately based on what's called the pigeonhole principle. So the pigeonhole principle is a statement that if you have a number of pigeons and they all have to go into pigeonholes, and you have more pigeons than pigeonholes, then one of the pigeonholes has to have at least 2 pigeons in it. So there has to be 2 pigeons that are close together. So, for instance, if you have 100 numbers and they all range from 1 to 1,000, 2 of them have to be at most 10 apart.
Mm-hmm.
Because you can divide up the numbers from 1 to 100 into 100 pigeon holes. Let's say if you have 101 numbers. If you have 101 numbers, then 2 of them have to be distance less than 10 apart, because 2 of them have to belong to the same pigeonhole. So it's a basic feature of a basic principle in mathematics. So it doesn't quite work with the primes directly, because the primes get sparser and sparser as you go out. That fewer and fewer numbers are prime. But it turns out that there's a way to assign weights to numbers. So there are numbers that are kind of almost prime, but they're not. They don't have no factors at all other than themselves and 1. But they have very few factors. And it turns out that we understand almost primes a lot better than we understand primes. And so, for example, it was known for a long time that there were twin almost primes. This has been worked out. So almost primes are something we can't understand. So you can actually restrict attention to a suitable set of almost primes. And whereas the primes are very sparse overall, relative to the almost primes, they actually are much less sparse. They may, you can set up a set of almost primes where the primes have density like, say, 1%. And that gives you a shot at proving, by applying some sort of pigeonhole principle, that there's pairs of primes that are just only 100 apart. But in order to prove the twin prime conjecture, you need to get the density of primes inside the almost primes up to a threshold of 50%. Once you get up to 50%, you will get twin primes. But unfortunately, there are barriers. We know that no matter what kind of good set of almost primes you pick, the density of primes can never get above 50%. It's called the parity barrier. And I would love to find, so one of my long-term dreams is to find a way to breach that barrier, because it would open up not only the twin prime conjecture, the go-back conjecture, and many other problems in number theory are currently blocked because our current techniques would require going beyond this theoretical parity barrier. It's like going faster than the speed of light.
Yeah, so we should say twin prime conjecture, one of the biggest problems in the history of mathematics. Go-back conjecture also. They feel like next door neighbors. Has there been days when you felt you saw the path?
Oh yeah, yeah. Sometimes you try something and it works super well. You again the sense of mathematical smell we talked about earlier. You learn from experience when things are going too well,
Yeah.
because there are certain difficulties that you sort of have to encounter. I think the way a colleague might put it is that like if you are on the streets of New York and you put in a blindfold and you put in a car and after some hours the blindfold is off and you're in Beijing. Um, I mean, that was too easy somehow. Like
Yeah.
there was no ocean being crossed. Even if you don't know exactly what was done, you're suspecting that something wasn't right.
But is that still in the back of your head do you return to the prime? Do you return to the prime numbers every once in a while to see?
Yeah, when I have nothing better to do, which is less and less times, which is I get busy with so many things these days. But yeah, when I have free time and I'm too frustrated to work on my sort of real research projects, and I also don't want to do my administrative stuff, or I don't want to do some errand for my family. I can play with these things for fun, and usually you get nowhere. Yeah, you have to learn to just say, okay, fine. Once again, nothing happened. I will move on. Yeah, very occasionally one of these problems I actually solved. Well, sometimes, as you say, you think you solved it, and then you throw it for maybe 15 minutes, and then you think I should check this because this is too easy, too good to be true, and it usually is.
What's your gut say about when these problems will be solved? When prime and Gobot?
Prime, I think we'll
10 years?
keep getting more partial results. It does need at least one. This parity barrier is the biggest remaining obstacle. There are simpler versions of the conjecture where we are getting really close. So I think in 10 years, we will have many more, much closer results. We may not have the whole thing. Yeah, so twin primes is somewhat close. Riemann hypothesis, I have no clue. I mean, it has happened by accident. I think.
So the Riemann hypothesis is a kind of more general conjecture about the distribution of prime numbers, right?
Right. Yeah. It's states that sort of viewed multiplicatively, like for questions only involving multiplication, no addition, the primes really do behave as randomly as you could hope. So there's a phenomenon in probability called square root cancellation that like if you want to poll, say, America on some issue, and you ask one or two voters, and you may have sampled a bad sample, and then you get a really imprecise measurement of the full average. But if you sample more and more people, the accuracy gets better and better, and the accuracy improves like the square root of the number of people you sample. So yeah, if you sample 1,000 people, you can get like a 2-3% margin of error. So in the same sense, if you measure the primes in a certain multiplicative sense, there's a certain type of statistic you can measure, and it's called the Riemann zeta function, and it fluctuates up and down. But in some sense, as you keep averaging more and more, if you sample more and more, the fluctuation should go down as if they were random. And there's a very precise way to quantify that, and the Riemann hypothesis is a very elegant way that captures this. But as with many other areas in mathematics, we have very few tools to show that something really genuinely behaves like really random. And this is actually not just a little bit random, but it's asking that it behaves as random as it actually random set, this square root cancellation. And we know, actually, because of things related to the parity problem, actually, that most of our usual techniques cannot hope to settle this question. The proof has to come out of left field. Yeah, but what that is, yeah, no one has any serious proposal. Yeah, and there's various ways to sort of, as I said, you can modify the primes a little bit, and you can destroy the Riemann hypothesis. So, like, it has to be very delicate. You can't apply something that has huge margins of error. It has to just barely work. And like, there's like all these pitfalls that you have to like dodge very adeptly. Yeah.
The prime numbers is just fascinating.
Yeah.
What to you is most mysterious about the prime numbers?
That's a good question. So like conjecturally, we have a good model of them. I mean, like as I said, I mean, they have certain patterns, like the primes are usually odd, for instance. But apart from these sort of obvious patterns, they behave very randomly. And just assuming that they behave, so there's something called the Kramer random model of the primes, that after a certain point, primes just behave like a random set. And there's various slight modifications to this model, but this has been a very good model. It matches the numerics. It tells us what to predict. Like, I can tell you with complete certainty the Trinity conjecture is true. The random model gives overwhelming odds it is true. I just can't prove it. Most of our mathematics is optimized for solving things with patterns in them. And the primes have this anti-pattern, as do almost everything, really. But we can't prove that. Yeah, I guess it's not mysterious that the primes be random. It's kind of random because there's sort of no reason for them to be to have any kind of secret pattern. But what is mysterious is what is the mechanism that really forces the randomness to happen. And this is just absent.
Another incredibly surprisingly difficult problem is the Collatz conjecture.
Oh, yes.
Simple to state, beautiful to visualize in its simplicity, and yet extremely difficult to solve, and yet you have been able to make progress. Paul Erdős said about the Collatz conjecture that mathematics may not be ready for such problems. Others have stated that it is an extraordinarily difficult problem, completely out of reach. This is in 2010, out of reach of present-day mathematics, and yet you have made some progress. Why is it so difficult to make? Can you actually even explain what it is?
So it's a problem that you can explain. It helps with some visual aids, but so you take any natural number, like say 13, and you apply the following procedure to it. So if it's even, you divide it by 2, and if it's odd, you multiply it by 3 and add 1. So even numbers get smaller, odd numbers get bigger. So 13 would become 40, because 13 times 3 is 39, add 1, you get 40. So it's a simple process. For odd numbers and even numbers, they're both very easy operations. And then you put it together, it's still reasonably simple. But then you ask what happens when you iterate it. You take the output that you just got and feed it back in. So 13 becomes 40. 40 is now even. Divided by 2 is 20. 20 is still even. Divided by 2, 10. 5. And then 5 times 3 plus 1 is 16. And then 8, 4, 2, 1. So, and then from 1, it goes 1, 4, 2, 1, 4, 2, 1. It cycles forever. So the sequence I just described, 13, 40, 20, 10, and so forth, these are also called hailstone sequences because there's an oversimplified model of hailstone formation, which is not actually quite correct, but it's somehow taught to high school students as a first approximation. Is that like a little nugget of ice gets an ice crystal forms in a cloud, and it goes up and down because of the wind, and sometimes when it's cold it acquires a bit more mass, and maybe it melts a little bit, and this process of going up and down creates this sort of partially melted ice, which eventually creates this hailstone, and eventually it falls down to the earth. So the conjecture is that no matter how high you start up, like you take a number which is in the millions or billions, there's this process that goes up if you're odd and down if you're even. It eventually goes down to earth all the time.
No matter where you start with this very simple algorithm, you end up at 1.
Right.
And you might climb for a while.
Right. Yeah. So it's
come down.
Yeah. If you plot it, these sequences, they look like Brownian motion. They look like the stock market. They just go up and down in a seemingly random pattern. And in fact, usually that's what happens. That if you plug in a random number, you can actually prove, at least initially, that it would look like random walk. And that's actually a random walk with a downward drift. It's like if you're always gambling on a roulette at the casino with odds slightly weighted against you. So sometimes you win, sometimes you lose, but in the long run, you lose a bit more than you win. And so normally your wallet will go to 0 if you just keep playing over and over again.
So statistically, it makes sense.
Yes. Yeah. So the result that I proved, roughly speaking, is such that statistically, like 99% of all inputs would drift down to maybe not all the way to 1, but to be much, much smaller than what you started. So it's like if I told you that if you go to a casino, most of the time you end up, if you keep playing for long enough, you end up with a smaller amount in your wallet than when you started. That's kind of like the result that I proved.
So why is that result, like, can you continue down that thread to prove the full conjecture?
Well, the problem is that I used arguments from probability theory, and there's always this exceptional event. So so in probability we have this law of large numbers, which tells you things like if you play a casino with a game at a casino with a losing expectation, over time you are guaranteed, well, almost surely, with probability as close to 100% as you wish, you're guaranteed to lose money. But there's always this exceptional outlier. Like, it is mathematically possible that even in the game is the odds are not in your favor, you could just keep winning slightly more often than you lose. Very much like how in Navier-Stokes, it could be, most of the time your waves can disperse. There could be just one outlier choice of initial conditions that would lead you to blow up. And there could be one outlier choice of a special number that you stick in that shoots off to infinity, while all other numbers crash to Earth, crash to one.
Yeah.
In fact, there's some mathematicians who've, Alex Kantorovich, for instance, who've proposed that that actually these collapse iterations are like these cellular automata. Actually, if you look at what they happen in binary, they do actually look a little bit like these game of life type patterns. And in an analogy to how the game of life can create these massive, like, self-replicating objects and so forth, possibly you could create some sort of heavier than air flying machine, a number which is actually encoding this machine, which is just whose job it is to encode, is to create a version of itself which is larger.
Heavier than air machine encoded in a number that flies forever.
Yeah. So Conway, in fact, worked on this problem as well.
Oh, wow.
So Conway, so similar. In fact, that was one of my inspirations for the Navier-Stokes project. Conway studied generalizations of the collapse problem, where instead of multiplying by 3 and adding 1 or dividing by 2, you have more complicated branch rules. But instead of having 2 cases, maybe you have 17 cases, and you go up and down. And he showed that once your iteration gets complicated enough, you can actually encode Turing machines, and you can actually make these problems undecidable and do things like this. In fact, he invented a programming language for these kind of fractional linear transformations. He called it FactTran as a play on Fortran, and he showed that you can program it with Turing complete. You could make a program that if your number you inserted in was encoded as a prime, it would sink to 0. It would go down, otherwise it would go up, and things like that. So the general class of problems is really as complicated as all of mathematics.
Some of the mystery of the cellular automata that we talked about, having a mathematical framework to say anything about cellular automata, maybe the same kind of framework is required.
Yeah.
For the Clock's conjecture.
Yeah, if you want to do it not statistically, but you really want 100% of all inputs to for the Earth. Yeah, so what might be feasible is statistically 99%, go to 1, but like everything, that looks hard.
What would you say is, out of these within reach famous problems, is the hardest problem we have today? Is the Riemann hypothesis?
Riemann is up there. P equals NP is a good one, because that's a meta problem. Like, if you solve that in the positive sense, that you can find a P equals NP algorithm, then potentially this solves a lot of other problems as well.
And we should mention some of the conjectures we've been talking about. A lot of stuff is built on top of them now. There's ripple effects. P equals NP has more ripple effects than basically any other.
Right. If the Riemann hypothesis is disproven, that would be a big mental shock to the number theorists, but it would have follow-on effects for cryptography. Because a lot of cryptography uses number theory, constructions involving primes and so forth. And it relies very much on the intuition that number theorists have built over many, many years of what operations involving primes behave randomly and what ones don't. And in particular, encryption methods are designed to turn text with information on it into text which is indistinguishable from random noise. So and hence we believe to be almost impossible to crack, at least mathematically. But if something as core to our beliefs as the Riemann hypothesis is wrong, it means that there are actual patterns of the primes that we're not aware of. And if there's one, there's probably going to be more. And suddenly a lot of our crypto systems are in doubt.
Yeah. But then how do you then say stuff about the primes?
Yeah.
Now you're going towards the conjecture again. Because if you want it to be random, right?
Yes.
You want it to be
Yeah.
randomly.
Yeah, so more broadly, I'm just looking for more tools, more ways to show that things are random. How do you prove a conspiracy doesn't happen?
Right. Is there any chance to you that P equals NP? Is there can you imagine a possible universe?
It is possible. I mean, there's various scenarios. I mean, there's one where it is technically possible, but in practice never actually implementable. The evidence is sort of slightly pushing in favor of no, that probably P is not equal to NP.
I mean, it seems like it's one of those cases similar to Riemann hypothesis. I think the evidence is leaning pretty heavily on the no.
Certainly more on the no than on the yes. The funny thing about P equals NP is that we have also a lot more obstructions than we do for almost any other problem. So while there's evidence, we also have a lot of results ruling out many, many types of approaches to the problem. This is the one thing that the computer scientists have actually been very good at. It's actually saying that certain approaches cannot work, no-go theorems. It could be undecidable. We don't know.
There's a funny story I read that when you won the Fields Medal, somebody from the internet wrote you and asked, what are you going to do now that you've won this prestigious award? And then you just quickly, very humbly said that, a shiny medal is not going to solve any of the problems I'm currently working on. So I'm going to keep working on them. It's just, first of all, it's funny to me that you would answer an email in that context. And second of all, it just shows your humility. But anyway, maybe you could speak to the Fields Medal, but it's another way for me to ask about Grigori Perelman. What do you think about him famously declining the Fields Medal and the Millennium Prize, which came with a $1 million of prize money? He stated that, "I'm not interested in money or fame. The prize is completely irrelevant for me. If the proof is correct, then no other recognition is needed."
Yeah, no, he's somewhat of an outlier, even among mathematicians who tend to have somewhat idealistic views. I've never met him. I think I'd be interested to meet him one day, but I never had the chance. I know people who met him. But he's always had strong views about certain things. Yeah, I mean, it's not like he was completely isolated from the math community. I mean, he would give talks and write papers and so forth. But at some point, he just decided not to engage with the rest of the community. He was disillusioned or something. I don't know. And he decided to peace out and collect mushrooms in St. Petersburg or something, and that's fine. And you can do that. I mean, that's another sort of flip side. I mean, we are not. A lot of problems that we solve, some of them do have practical application, and that's great. But like, if you stop thinking about a problem, so he hasn't published since in this field, but that's fine. There's many other people who've done so as well. So I guess one thing I didn't realize initially with the Fields Medal is that it sort of makes you part of the establishment. So most mathematicians, they're just career mathematicians. You just focus on publishing the next paper, maybe getting promoted one rank, and starting a few projects, maybe taking some students or something. Yeah, but then suddenly people want your opinion on things, and you have to think a little bit about things that you might just sort of foolishly say because no one's going to listen to you. It's more important now.
Is it constraining to you? Are you able to still have fun and be a rebel and try crazy stuff and play with ideas?
I have a lot less free time than I had previously. I mean, mostly by choice. I mean, I can always see I have the option to sort of decline So I decline a lot of things. I could decline even more, or I could acquire a reputation of being so unreliable that people don't even ask anymore.
I love the different algorithms here. This is great.
It's always an option.